In this video, we're going to continue on with Chapter 8, and specifically we're going to focus on Section 8.3, which is a confidence interval for mu. Now, we've done a confidence interval for p, okay, and it's going to be very similar to mu, and so hopefully, definitely this video is going to be a lot shorter, okay, and hopefully will make some sense, probably more sense than that first video made, okay. So again, general form of a confidence interval that we're going to use, point estimator plus or minus the margin of error. Okay. In this case, our population parameter is now mu, the population mean. Before it was p, the population proportion. Now it's mu, the population mean. Our point estimator, what we're using to try to estimate mu, is of course the sample mean, x bar. Okay, so the sampling distribution of x bar, which we talked about again in Chapter 7, is this. Okay, there are some different cases, but we're not really going to worry about those cases. The sampling distribution of x bar is this. It's also approximately normal, just like p hat. Okay, that we discussed in the last video. It's approximately normal with a mean of mu, standard deviation of sigma divided by the square root of n. And of course, this depends on the sample size or population distribution. So again, those were the two cases. If the population distribution was normal, then x was also normal. Or we had the central limit theorem, which guaranteed us that if if the sample size is large enough, then x would tend to normality. Okay. So, using the same logic as before, when we did confidence intervals for p, the confidence interval for mu is the point estimate plus or minus confidence level times standard error. Okay, and so we just pull the parts of the formula from different places now, but it's the same formula. Okay. Again, we have that problem that we don't know the population version of everything. So I don't know the mean, the population mean, okay, mu, and so it's very likely that I also don't know the population standard deviation. Okay, so I very likely don't know anything about the population. So I don't know sigma. Mu doesn't make itself known in this formula, which is good, but sigma does. Sigma is there, and so I need to replace it. And so I replace it with the sample version. The population standard deviation is sigma. The sample standard deviation is S. Okay. Now, when this happens, something important happens. Okay. It was a really nice case when we replaced p with p hat in the confidence interval thing before, but now when we replace sigma with S, the distribution that we use changes from a normal distribution to something called a t-distribution. Okay, so you may or may not have read about the t-distribution in our readings. Okay, but let's look at the t-distribution. So it's a continuous distribution that's very similar to the normal distribution, but it has what's called fatter tails. And so properties of the t family of distributions are this. It's symmetric and it's bell-shaped, just like the normal. Okay? But in addition, it's also always centered at 0. The normal distribution is centered at mu. The t distribution is always centered at 0. Okay? It's parameterized not by a mean and a standard deviation anymore, but by something called degrees of freedom, which have been discussed in your readings. Okay, and we'll discuss what it means in this context. We denote the t distribution with a lowercase t, okay, and then in the subscript it has its parameter degrees of freedom. Okay? An important thing to keep in mind with the t-distribution is as the degrees of freedom increases and gets really large, it starts to look like a standard normal distribution. So it starts to turn normal. And it has a functional form, okay, but it's ugly, and so we don't need to look at it right now because it doesn't do us any good. As a visual representation, the t-distribution is in red, the normal distribution is in blue here. Okay, so the t with 1 degree of freedom versus a standard normal distribution. Both are centered at 0, but as you can see, as you go farther and farther out, the red curve stays higher than the blue one. So you would say that the blue one is more peaked. Okay, it peaks more at 0 and then falls away faster than the t. So now the correct interval is this. Okay, so I made that change from sigma to s, and something big happened. Now instead of using a z, I'm now using this t. Okay, so this is going to be a t confidence level number. And so the confidence factor that I find is a t that is something from the t distribution with n minus 1 degrees of freedom and alpha over 2 leveled to the right. Okay, so keep that in mind. T distribution with n minus 1 degrees of freedom, alpha over 2 area to the right. The assumptions for the confidence interval are, again, that the data is obtained by some form of randomization, whether it's random sampling, so on and so forth. And the one that's different now is that the population distribution is normally distributed. Okay, so that's an assumption that we need, sort of. Okay, it turns out that you can violate that assumption to a certain extent without facing problems, theoretically. Okay, so usually in the problem it will state this, that the population distribution is normally distributed. If it doesn't, you assume that it's true and you move forward. Okay, I will show you later on in the course how to actually assess if it looks like the population distribution is normally distributed. So again, here is a setup. Suppose it's known that people talked on their phones for an average of 21 minutes per day. Researchers want to know if having such easy access to cell phones has changed the amount of time that people talk on a phone. Okay, so again, this question is kind of old, as you can see, but this was more germane when cell phones started to really take off. Thus, they would like to estimate with 95% confidence the average number of minutes that people talk on a phone, cell phone, or land phone. There's almost no such thing as a land phone anymore, but phone. Okay. Suppose a random sample of 40 people is polled, and the mean number of minutes talked on the landline is 24 minutes with a standard deviation of 5. Okay, estimate with 95% confidence the average number of minutes that people talk on a phone. So, again, I have the work written out for you here. Sorry, I'll move through here. Okay, so again, same problem. First step also is to find the parts of the equation that we can from the setup. We know that the sample size is 40. Okay? We know that the sample mean is 24, and we know that the sample standard deviation is 5. And that gives us almost everything. Again, the last thing and sort of the hardest thing to calculate for these problems is that confidence factor. Okay? And it's a t distribution with n minus 1 degrees of freedom, alpha over 2 to the right. So first we need to find alpha. Alpha is 1 minus the confidence level as a decimal, so alpha is 0.05. Okay, and so that means 95% lies inside, 2.5% lies on each side, so the number that I'm looking for is 0.975 again, okay, like we saw before. So let's go to Minitab and see how this differs from when we did it with the normal distribution in the last video. So we're going to go to Calculate Probability Distributions, again inverse cumulative probability, okay. And the only difference now is that instead of a normal distribution, we're going to use the t. So down here is the t. Okay. It asks for degrees of freedom, and degrees of freedom is n minus 1. N was 40, and so the degrees of freedom is 39. And there's also this thing called a non-centrality parameter, but you don't need to worry about this. Okay. Technically, you could enter a number in here other than 0, and that would move the t-distribution to not have a mean of 0, but a mean of something else. But we want a mean of 0, so we stay there, and then the value appears 0.975, okay, based on what I just said. So when I click OK, the number that comes out is 2.02269, and I'll round that to 2.023. Generally, I'll round z-scores to 3 decimal places, unless they're sort of special, and then I'll round them to 2 decimal places. So 2.023. So that's where I got this number here. So again, I have all the information I need. I substitute it into my simple equation up here. Okay, write out the numbers, and then I come down here. Here is my interval, 22.4 to 25.6. And again, I need to interpret the interval. Anytime you calculate a confidence interval, you need to include an interpretation. Okay? You will lose points if you do not include an interpretation. So it's that I am 95% confident that the true mean number of minutes talked on the phone is between 22.4 and 25.6 minutes. Again, I start out with I am blank percent confident. Then I take it exactly from what I'm creating the confidence interval about is my next part. And then I say is between blank and blank minutes. And so that's how you create a confidence interval for mu. So if we move back here, here is the second your turn, okay, or the first your turn for this video. I again put a simple setup here, and I want you to compute a 99% confidence interval. Okay, so hopefully that shouldn't be too bad.